So hello everyone, welcome to this video. So in this video, solve we will solve five problems based on shell momentum balance. Okay, and in all those problems, what we have to do, we have to either find the velocity profile or the flux profile, the momentum flux, or the parameters which can be calculated by using those flux profile or velocity profile. Okay, so this is our task for the today's video. Okay, so first of all, I will give you a basic approach that how to deal with the questions in which the flux profile and the velocity profile is asked to find, and I will give you a certain set of steps and certain set of conditions which you can use to easily solve any problem on velocity profile and flux profile. So so let's first, I will give you a brief intro that what is shell momentum balance. Okay, and note one thing that we will solve all problems at steady state. So, what is steady state? We all know steady state means there is no change in properties with time. Means with time, the properties like velocity or the force acting on the body or anything like that is constant. Okay, so first of all, let's understand that what is shell momentum balance. Okay. So as the name suggests, shell momentum balance means the balance of momentum across a shell. Okay. So now here, shell momentum balance. So balance it means what? Suppose this is a shell, then some momentum is coming in, some momentum is going out, and some momentum may be present inside the shell. So the balance of this momentum comes in the topic of shell momentum balance. Okay. So here what is written that if you see here, this one, rate of momentum in by convective transport, rate of momentum out by convective transport, minus is there. Then rate of momentum in by molecular transport minus rate of momentum out by molecular transport plus force of gravity acting on the system equates to zero. Okay. So when we will solve the questions, I will try to explain each and every term in the shell momentum balance. Okay. For now, I advise you that you just go through it once. Okay, then so this is a momentum balance which we have to apply almost in every question in which momentum flux or velocity is required to find. Okay, then this now there is a basic approach or means this is a verified approach, means if you will follow these 8 steps, you will be able to solve any questions of shell momentum balance. Okay, so let's go through these steps one by one, and we will explain this by questions. Okay, so what is first step? Select the coordinate system and the origin. Then identify the non-vanishing velocity component and the variable on which it depends. Non-vanishing velocity component means we have to find the components of velocity such that those are non-zero component. Suppose a fluid is moving in z direction, so it's the x component of the velocity will be zero and y component of the velocity will be zero. Okay, so non-vanishing component of velocity will be vz. Then we have to write a momentum balance. How to write a momentum balance? We have seen just now this. This is what? Momentum balance. Okay. Then what is next step? Let the thickness of the shell approaches to zero. Okay. And make use of the definition of the first derivative to obtain the corresponding differential equation for the momentum flux. So when I will explain you the question, I will tell you that what is this first derivative, this definition of first derivative means. Okay. Then integrate the equation to get the momentum flux distribution. So, when you will get a differential equation in momentum flux, for example, you get d tau by tx equates to some constant value. Then, if you will integrate using some boundary condition that will be given in the question, you may easily get momentum flux profile. So that is what is said in this fifth point. Then insert Newton's law of viscosity and obtain a differential equation for the velocity. So we all know what is Newton's law of viscosity. It states that momentum flux is directly proportional to the velocity gradient. Okay. So suppose you have calculated the velocity, the momentum flux profile. Now, if you will, substitute the value of momentum flux, which is in the form of velocity gradient, and then integrate the equation, you will easily get the velocity profile. That is what is written over here. Insert the Newton's law of viscosity, obtain a differential equation, then integrate this equation to get the velocity distribution by using some conditions. Okay. So 6 and 7 point is clear. Now use the velocity distribution to get other quantities such as Vmax or V average. V average means the average velocity of the fluid. Then force on the solid surface. So basically, when you will go for practical application, the more important parameters which we need to evaluate are average velocity or maximum velocity, or the position of maximum velocity. But those parameters will be evaluated only when you have the velocity distributions or the flux distributions. So for evaluating those parameters, we first need to find the velocity distribution and the flux distribution. Okay. So that is why shell momentum balance is necessary. So now we will start one by one. Okay. Now we will move to question number one. Okay. So this is question number one. Actually, this is a unsolved problem of BSL also, and you may easily find in the book also. I have written over here also. So what it states? Let us first read a question, then we will see the diagram, and then we will try to solve it using shallow imbalance. Okay. So the title of the problem is laminar flow in a narrow slit. So a Newtonian fluid is in laminar flow in a narrow slit formed by two parallel walls a distance 2b apart. So basically, uh, what is written over here, that there is a fluid which follows Newton's law. That is why it is known as Newtonian fluid. It is flowing in a narrow slit. Narrow means thin. So basically, suppose this is my slit. So the distance between these two boundaries is very less, and such that it is very thin or it is very narrow. Okay. And the flow is laminar. Okay. Then such that B is much less than W. So B is basically the thickness of the wall, or you can say the distance between the two boundaries, and W is basically the width. So it is given that this B is much less than W. So and effects are neglected. Okay, then what we have to do? Make a differential momentum balance and obtain the following expression for momentum flux and velocity distribution. So when we will apply the shell momentum balance, we will get some momentum flux profile and velocity profile. So we have to derive that our momentum flux profile will be like this and velocity profile will be like this. And here P is what? It is given in the question. Here P is P minus rho g z. Okay. Where Z is what? Z will be our height from the top of the, you can say, slit. Okay. Then what is B part? What is asked in the B part in the question? Let me zoom it out. What is the ratio of average velocity to the maximum velocity for this flow? Okay. Then obtain the slit analog of Hagen-Poiseuille equation. So I will explain you that what is this Hagen-Poiseuille equation also. So this is my diagram. Okay. So you can see here fluid is flowing from in this direction. Okay. This is my slit. Here 2b is the thickness of the slit, or you can say the distance between the two boundaries b1 and b2. Okay. W is the width of the slit and L is the length. And this is how I have selected my coordinate system. This is I have selected which coordinate system? Cartesian coordinate system. Okay, because it is seen that it is in the form of rectangle, and it is and the my problem can be easily solved by using Cartesian coordinate system. Okay, so this is my problem. So first of all, I will be mentioning that what is given in the problem. First one is what? It is laminar flow, means 1D flow. Okay. Now how it is 1D flow? See, you can easily see that if I have defined my coordinate system like this, like y is in this direction, z is in downward direction, and x is in my right direction, then the flow is in only downward direction. Means here Vx means the velocity of fluid in x direction and the velocity of fluid in y direction is 0. So only the so what was my step number one is to select the coordinate system and origin. Okay. So this I have already selected. Let me yeah. So this I have already selected. I have selected my which coordinate system I have selected, Cartesian coordinate system, and I will select my origin later. Okay. Then what was the second step? Identify the non-vanishing velocity component and the variable on which it depends. So non-vanishing velocity component. Since I have defined the Cartesian coordinate system, so here according to this, velocity of the fluid in x direction is 0 and velocity of fluid in y direction is 0. So the remaining non-vanishing velocity component is my vz. Okay. Now I have to define the variable, or you can say the dimension, or you can say the direction on which my vz depends. Okay. So now let let see what is given. What else is given? That edge effects are neglected. Okay, and make an assumption over here that okay. So what is given that vz is only vz, only the velocity in z direction is there. Okay. So if I have assumed that edge effects are neglected, means when the fluid will flow, there will be some disturbances. Let me change the color. Yeah. So when the fluid flow, there will be some disturbances at the start of the flow and at the end of the flow. So in problem, it is mentioned that we have to neglect these, and this distribution means it is given that Vz, yeah. So it is given that Vz at z equals to 0. If I have assumed my origin over here, means at z equals to 0, this is my z equals to 0, and this is my z equals to L, then Vz at z equals to 0 will be, I can say that Vz at z equals to 0 is Vz at z equals to L. How can I say this? So the question comes that there is a gravity will be acting in downward direction also. Okay. So if my acceleration is there in downward direction, then my velocity must be increasing downward direction. But what we will assume that this this force of gravity will be dominated or will be compensated by the viscous force which will act in the direction opposing to the motion. Suppose, as my direction of motion is in the downward direction. Okay. So what I will assume that my viscous forces will act in the direction opposing to the direction of motion, and this effect of gravity will be neglected by the viscous forces. So there will be no net acceleration in the z direction, means velocity will be constant, means this vz will be constant in z direction, means there will be no variation, means vz will not be a function of z. This vz will be constant in z direction. Okay. Now other two directions are x and y. Okay. So it can be easily seen that in y direction all fluid particles will have same velocity only. Suppose you have chosen the y coordinate over here. Okay. Here. This is my suppose delta y direction. So all the fluid coming in this small delta y will have same velocity only. So my vz will not be a function of fy or y also. Then comes what is x. Okay. Now let me rub all this. Yeah. So okay. So where we were now we have understood that vz is not a function of x, sorry, not a function of y and z. Okay. Now comes x term. So let me rotate this slit, and suppose this is my slit. Sorry. Okay. Uh, so this is my slit. The fluid is moving in this direction. Okay. This is my x z direction, and this is my x direction. Okay. and these are the layers of fluid. Okay. So now understand, velocity is constant in z direction. Okay, but see, these walls are having zero velocity. Means this wall is having the velocity zero, and the velocity of this wall is also what, zero. Okay, so the tendency of this wall on the layer of the fluid which is just adjacent to it. Suppose this red layer is in contact with this wall, and this red layer is in contact with this wall. Means the very next layer after the wall is my red layer of the fluid. I hope you understand this. Okay. So the tendency of this wall on this layer of fluid will be such that it will force the layer of the fluid to be in stationary motion only. Means, or no motion only. Means the velocity of the fluid of this layer of fluid will be zero. This is what is known as no slip condition, which will be used as a boundary condition when we will solve the momentum flux and the velocity profile. And same here, the velocity of the fluid this layer will also be zero. But we know that fluid is moving, so this the layers of fluid at the center, or here it is moving. So I can correlate that the velocity of fluid in x direction is not constant. Here velocity is zero. Here I can assume that velocity is maximum because this is at center, and this is what my velocity flux velocity profile is expected. Somewhat like this. Means my vz, my velocity in z direction, is a function of x. Means from here, if I choose one x1 and x2, the velocity at x1 will not be equal to velocity at x2. The reason behind this is viscous forces are acting in the direction of x. So due to that viscosity between the layers of the fluid, the velocity of two layers are not same. So my Vz is a function of x. Okay. Then what was the third step? Is now we have to simply write a momentum balance, and when then it's all mathematics. Okay. So let's proceed. So we have identified that Vz is a function of x and not a function of z and neither y. And my Vx and Vy are zero. Okay. So see, as there is motion in only in z direction, so I will take only my z momentum flux. Okay. So this one I have only considered what phi z as there is motion only in z direction. Now phi z will have three components: phi xz, phi yz, and phi zz. Okay. And I hope you know that total momentum flux phi can be written as pressure flux, pressure plus rho v1 v2. If I am written it as one of 2 plus tau 1 2. Okay. This is more what my convective flux. This is by conduction, and this is what pressure. Okay. So this is what total momentum flux is written as over here. Mhm. So now what I will do, I will consider a shell. Now, as my velocity is varying in x direction, okay, so my dimension of shell will be such that I will choose a small element in x direction. Okay, as things are varying with x, so I will choose a small element delta x, and I will assume that in that delta x my things are constant, my velocity may be constant, so I can apply a shell momentum balance. So this is what is written over here. I have assumed the shell whose width is nothing but w only. Okay, length is l. As things are constant with l and w, as velocity is neither a function of y or neither a function of z, it is only function of x. Okay, so simply we will write a momentum balance. So I in momentum balance, what we write is rate of momentum. Okay, and this is what? Phi is what? Momentum flux. So how I can get rate? My rate will be equal to what? Flux times area. Okay. And which area? The area perpendicular to the direction of flow. So if I am writing phi xz means z momentum flux in the direction of x. So I will have to take the area which is perpendicular to x means area corresponding to y and z axis. So what is the area corresponding to y and z here? This is my sorry. So this is my z direction downward and this is my y direction. This one. This is my z direction and this is my y direction. In z direction, the length is L, y direction is W. So my area will be for phi xz will be what? LW. Okay. And you know, so I have told you that in shell momentum balance, there are two terms was there. One one was convective and other one was conductive. So let me tell you, convective means the rate of the or you can say the convective momentum means the momentum or the rate of momentum which is which is there because of the bulk motion of the fluid. So here if you will see the bulk motion is in the z direction. Okay. So the z component of the total momentum will be my convective momentum rate and the conductive momentum is in which direction? In which viscous forces are acting, which was my x direction. So the you can see here viscous forces are acting in x direction. So the x component of my z momentum is my conductive momentum rate. Okay. So what is the rate of conductive momentum? Which is phi xz. Conductive means molecular transport due to my viscous forces here. So phi xz and it is my inlet. So I have designed a shell such that its dimension is x to x plus delta x. Okay. And I have considered origin over here. You can choose origin over here also, at the edges also. Okay. It's your choice. Okay. So what is the rate of conductive momentum? It is phi xz at x equals to x into Lw. Conductive momentum out is phi zz at z equals to 0 into W into delta x. Convective momentum. Convective means bulk flow. Bulk flow is in the direction of z. Okay. And inlet is my this. This is the inlet. And the area perpendicular to z is W times delta x. This one. I hope you are understanding. This is what delta x and this is what my W. The direction of the bulk flow is this one. So the area perpendicular to this will be area corresponding to y and z, which is nothing but which is nothing but W into delta x. So here phi z at z equals to 0 W delta x. Similarly, convective momentum out and conductive momentum out and convective momentum out is written. Okay. Now in that balance, the any other forces, if there are any other forces acting on the body, are need to be considered. So if you will see here, as we are considering the z momentum and in z direction gravity is acting. So it is an external force for our system. Okay. So how much force is acting? Gravitational force is mass into acceleration. So what is mass? Volume into density. And what will be the volume of this shell? This is a cuboid of length L, width W and thickness delta x. So L W delta x will be my volume, which by which I will multiply with the density. I will get mass. So W L delta x. This is my mass, and this is z. Dz is the acceleration due to gravity in the z direction. So I will get W L delta x rho g. This is my force of gravity acting on the system. Now I will put all these five terms in the shell momentum balance. Okay. This is what my conductive momentum in, convective momentum in, conductive momentum out, convective momentum out, and external forces. This equates to 0 at a steady state. Okay. Then what I will do, the coefficients of this phi xz is Lw, W delta x, Lw, W delta x, and here it is W L delta x. So I will send all this to our right hand side and divide it by W L delta x, and I will get this one, this expression. Okay, that phi zz at x plus delta x minus phi xz at x upon z. Sorry, this will be x. Okay. Now let's see what was our next step. Let the thickness of the shell approach zero and make use of the definition of the first derivative to obtain the corresponding differential equation for the momentum flux. Okay. So here, what thickness I have considered for the shell? Delta x. Now they are saying approach the thickness of the shell to be zero and apply the first derivative definition. So let me tell you what is the definition of the first derivative. So if there is a function which is the function of x, and if delta x tends to 0 and I am calculating f of x plus delta x minus f of x upon delta x, then I can equate it to dou df by dx. This is my this is a derivation of the definition of the first derivative. Okay. So here, if you will see, phi xz is a function of x. Okay, and I am evaluating this at x plus delta x divided by delta x. So if I do that delta x tends to 0, so what this will become? D phi xz upon dx. This is what x. Okay, so and this will remain as it is. Okay, this is equals to rho g. Now, what I will do, I will put the definition of phi xz and phi zz from here, which I have written already, phi xz and phi zz. Okay, so phi xz is what? Tau xz. Tau is what? Shear stress. And x and this z representing what? X representing the motion and z representing the direction of flow. Okay, means the shear stress of z in the direction of x. I hope you understand this. And phi zz. Phi zz is what? Rho vz plus p. Okay, so just simply substitute the definition in this equation. So what I have got here, d tau xz by dx. This is what my shear stress plus phi z at z equals to L. This is what PL means pressure at L, and what rho Vz at and into Vz at z equals to L minus pressure at 0 minus rho Vz into Vz at z equals to 0. And I have told you already that Vz is not a function of z, means velocity at z equals to 0 in z direction and velocity at z equals to 0 at z equals to L in z direction is constant, means I can simply cancel these terms. Okay. Now what I will get only PL and this rho g when comes to LHS side, just simply divide and multiply it by L, and this take this 1 by L common. So you will get PL minus rho GL minus P naught minus rho G 0 upon L. And we have given, if you will, and if I wrote the question correctly, it is given in the question that my capital P is what? P minus rho G Z, means if I have to write P capital PL, this is what? Small pl minus rho gl. Okay, so I have replaced this pl, small pl minus rho gl with capital PL and small p naught minus rho g0 with capital P naught. And for time being, I have assumed this to be a term as this is constant only, delta P. Okay, and this is what L. So this is what? This is my differential equation for what? Momentum flux. Okay. Now I will simply integrate it. So I will get tau xz is delta p x by L plus C1. Now I think we should discuss all three boundary conditions which we will be using in this question also and in all questions of shell momentum balance. Okay, to find the constant value. I have to find this C1 value. So I must know some condition which here what are the variable is tau x and x. So I have to know one condition of x and tau xz, means I have to know at least one value of x for which tau xz is known, so I can easily calculate my C1. Okay, so let's move on, that what are those boundary conditions. So if you know any problem is there, and when you will approach such problem, there are basically three boundary conditions. First one is no slip condition, which I have discussed earlier also, that if if there is a ball and the fluid layer which is just adjacent to the ball, they both will have the same condition, same velocity. Means there will not be any slip between these two layers. What is this? This is a just adjacent layer close to the ball, and this is what the ball only. Okay, so the relative velocity between these two will be zero. Means the velocity of the ball will be equal to the velocity of the layer of the fluid just adjacent to it. So this is what no slip condition. Then liquid interfacial plane or modified no slip condition. Okay, so suppose there is a slit, and in the bottom part oil is flowing, and in upper part, sorry, in bottom part water is flowing, and in upper part oil is flowing. Okay, now what this condition says that at the interface of the liquid and oil, okay, at interface what will happen? Suppose this is the interface. Okay, so the last layer from top, the last layer of the oil and the first layer of the water will be in contact with each other, and it says that there will not be any slip between these two layers. Means the velocity of the last layer of the water, the last layer of the oil and the first layer of the water will be same. Means the velocity of this and the velocity of this will be same. So this is what is second condition says. And third one is liquid gas interfacial plane. Okay, means zero flux condition. So as we know, the viscosity of the gases are much less than that of liquid. Okay, and the shear stress or the momentum flux, it depends on the viscosity of the fluid. So if the viscosity of one fluid is much less than the viscosity of the other fluid, so so in such condition there will not be any flux, and if it is any, we will neglect it. Means at liquid gas interface, our tau xz is zero. Means and what tau xz consists of? It consists of the velocity gradient. Means our velocity gradient will be zero at gas, liquid, or you can say liquid gas interfacial plane. Okay, so these three are the boundary conditions which we will using again and again in our problem. Okay, so now simply we will use our third boundary condition, that at x equals to 0, x equals to 0 is here. So if you will observe what is here over here, it is the liquid and gas interfacial plane. So here flux will be 0. So simply at x equals to 0, my tau xz is 0. So I have got C1 which is equal to 0. So this is what my flux profile, momentum flux profile. Now I will insert the Newton's law of viscosity. What is Newton's law of viscosity? That tau xy is minus mu dou vy by dou x. Means the shear stress is proportional to the velocity gradient. Okay, so tau xz is what? Minus mu dou vz by dou x, means variation of velocity in z with x direction. Now I simply integrate it, and I know that no slip condition, that at x equals to minus b or plus b here. These two walls are stationary. So the velocity of the fluid, of the velocity of the layer of the fluid which is in contact with this layer and this layer will be 0. And if I consider my origin here, so this is what plus b and this is what minus b. So at x equals to plus minus b, my velocity will be 0. So I will get C2, and here I will get what? My velocity profile. So once you have calculated this velocity profile and flux profile, now you can find any parameter you want in the problem. For example, I have asked to find the ratio of average velocity to the maximum velocity. So, I will easily find my average velocity by taking area average, as I am calculating the velocity in z direction. So, I will take the area perpendicular to z direction, which is what? X and y. So, simply vz dx dy upon dx dy. X varies from minus b to b, y varies from 0 to w. So, I have got what? V average here. And I know that vz max, where vz max will be, where my this vz will be maximum. So I can easily see that at x equals to 0, my vz will be maximum. And where this x equals to 0 is? At the center of the slit. Here. And when we were expecting a velocity profile, we have assumed, we were expecting that the velocity profile will be like this only, that velocity will be maximum at center, and then it will continuously decrease till the ends and finally become zero here. Okay. So the results are, are as expected as we were expecting. So simply I have got Vz means V average and Vz max, and I can simply find the ratio. And what is this Hagen-Poiseuille equation? So whenever you have asked to find the Hagen-Poiseuille equation, simply find the mass flow rate. Now what is mass flow rate? Mass flow rate is what? Kg per second. Kg is what? Meter cube per second, means volumetric flow rate into density. Now how you can find this volumetric flow rate? Simply area multiplied by average velocity. Now I have just calculated my average velocity over here. I know the area through which my fluid is flowing, which is what? 2bw. My velocity is this, my density I know rho. I have simply found the mass flow rate, which can be represented as m. Okay. So this is how we have solved the first problem. Okay, I hope you have understood this. You can take notes if you want. Now we will solve four more problems. Okay.